In the last video, we looked at closed sets. The definition for us is that a set in a metric space is closed if its complement is open. So we worked through enough examples that you might have a pretty good feel for what closed sets look like. But in this lesson, what we're going to do is define a type of point relative to a set. So we will work through the notion of accumulation points, and then we will see how accumulation points gives us an alternative way to assess whether or not a set is closed, one which is pretty practical and useful. Okay, so let's look at this definition. I'm going to read it out in words. I always do this kind of awkwardly because I think this definition is sort of strangely phrased. I'll sketch a picture and then I will give you what I think is a nice alternative way to phrase the ending of this definition. Okay, so a point X in the metric space, so just X in M, is an accumulation point of some set A if every open neighborhood of X contains a point of A which is not X itself. Okay, so that's the definition, but I think it's sort of just a big sentence. So we'll work through what this means. Let me make a couple remarks before we do that. I emphasized this as I stated this definition out loud, but X is just a point in the metric space. Notice there's nothing in this definition that requires X to be in A or not in A. So it could be either. So X does not need to be in A. And then the other thing I want to mention before we move on is that I use the phrase accumulation points, but these are often called limit points. And a very closely related notion is cluster point. So you might be looking at a different name for this kind of point in different context, but that's once you kind of learn accumulation points, limit points, it's usually pretty clear what's being referred to. Those names, accumulation, limit, cluster, they kind of tell you what's going on. So we will actually talk about this type of point like in several different contexts. This is just our first look at it. Okay, so what is an accumulation point? This definition is saying that if I have some point X and I draw any kind of open set around it, so let's say this is just a random open set U, it must be the case that somewhere in this open set U is a point from the set A, let me call it little a, which is not X itself. So I never want to be like, look, U contains X and X belongs to A. Doesn't matter. You need to pick up a different point. Okay, to go along with this beautiful picture, let me give you like a quantifier version of the ending of this definition. Normally, I actually prefer to see definitions and theorems written out in words and not just like with a string of logical symbols, but this is the one exception to that personal preference. I'm going to translate this idea that every open set of X contains a point from A, which is not X, into symbols which I prefer. Okay. Every open set U, in this picture here, I made U kind of lopsided shaped. It would be equivalent to say every epsilon neighborhood of X contains a point from A, which is not X. I'll let you think through why, but it's enough to give our open neighborhoods that kind of shape. So let me say that the ending of this definition could be phrased as, for all epsilon greater than 0, the epsilon neighborhood around X, so I'll write the ball around X of radius epsilon, take away X itself. So what I'm going to do is puncture this neighborhood by basically popping X out of the middle of it. So this neighborhood, which does not contain X, has a non-empty intersection with A. All right. So again, here I've given the idea of every open U, the structure of an epsilon neighborhood. That's just because I like to have concrete ideas to work with, and I just prefer epsilon neighborhoods in general. But if you wanted to, you could just take this beginning and say, for all open sets U containing X, you take away X has non-empty intersection with A. That would work too. I just prefer this. Okay, so for every radius, positive radius epsilon, if I take, let's draw a new picture, X, and I draw the open epsilon neighborhood around it, and then I basically take X out of the middle. Okay, that is the punctured neighborhood. This has non-empty intersection with A means, just like in this picture, I have to be able to find a point. Oh, that marker is not too visible. A point which lives in A. I think at this point, it's probably pretty clear why this covers the ending of this definition. By taking X out, I'm saying the point that we're picking up that lives in A isn't X. Um, so yeah, I think we're good to go with the definition. What we're going to do now is work through about 8 examples. I'm going to give you sets. Most of them are probably on R, but we'll look at a few different spaces. And for these sets, we want to find all accumulation points. So we might grab points kind of one at a time for a while until we can put it all together and say that for this example set, here's the family of accumulation points for that set. Once we've done enough of that, I think you'll have a pretty good idea of what an accumulation point looks like. We will look at a way to characterize closed sets using accumulation points, and this gives us a very useful way to assess whether or not a set is closed. Let's start with 4 examples from the Euclidean real number line R. Our first example is the interval from 0 to 1, including 0 but not including 1. Then we have the set of rationals, the set of integers, and then the set here that I call the Archimedean set. Okay, let me do the first one. Just going to do this with a picture. I want you to be building up a feel for what an accumulation point looks like. Okay, if I sketch a picture of this set, here's the number line. And we have 0 up through, but not including 1. We want to identify all points on R. Remember, they don't have to belong to the set, which have the property that every open neighborhood around them scoops up some point from this set, which is not the point that we drew the neighborhood around. Okay. So let me just kind of run through a couple different scenarios. Let's say that we are to the left of 0. So let's go left to right. If I'm down here, anywhere smaller than 0, I can design a specific open neighborhood which does not intersect the set in question. In particular, if I'm down here at some negative number, let the radius epsilon cut, say, halfway back to 0. This neighborhood has empty intersection with the original set, so nothing to the left of 0 is going to be an accumulation point. So we remove them from consideration. What about 0 itself? You probably came to the answer pretty quickly, which is that 0 is an accumulation point. If I take 0 and I draw any kind of open neighborhood I like around it, my open neighborhood is going to have to go to the right a little bit. And as it does, it's going to scoop up points from the set, which are positive, so they're not 0 itself. So these points in here live in the intersection of the original set and, say, this punctured neighborhood if I took 0 out of the middle. So 0 is an accumulation point, and in a similar way, any point in here is also an accumulation point because all neighborhoods that we draw around those sets contain other points from the set. I drew these neighborhoods kind of small, but I didn't need to. Notice around, say, this point here. So here's my point I'm considering. I could also draw a big neighborhood which contains points from the complement. That's not a problem. So we're not saying that all points have to belong to the set. We just need to be able to find one. So if this is the center point and this is the neighborhood, I still have choices for points which live in the intersection of the neighborhood and the original set. Doesn't matter that not all points have this property. Okay, what about 1 itself? 1 is not in the original set. If I draw an open neighborhood around 1, do I pick up points from the original set? That's the question. The answer is yes. So if I go like this, any open neighborhood I draw around 1 must pick up points to the left. It works the same way as 0 did. It doesn't matter that 1 doesn't belong to the set. You kind of want to ignore that point. So 1's not in the set, doesn't matter. To the left, we pick up points from the original set with any neighborhood we pick. So 1 is also an accumulation point. What about to the right of 1? Well, out here, it's just like when we started back here all the way to the left. I can design a neighborhood that has no overlap with our original set. So nothing kind of to the left of 0 or to the right of 1 is going to be an accumulation point. Okay, putting it all together, the set of accumulation points, I'll just call these APs, is the closed interval from 0 to 1. So it starts here, goes up through, and includes 1. Okay, I just worked through that example, so I'll let you pause and take a moment to address the set of rational numbers. Okay, for the set of rational numbers, I hope you got all of R as your final conclusion for the set of accumulation points. I will again draw a picture, but it's not going to be nearly as elaborate of an argument. So once again, let's just say this is the number line. Let X be any point in R, and I don't want to specify rational or irrational, it doesn't matter. Suppose this is just some random real number, and I draw any kind of open neighborhood around it. I usually like epsilon neighborhoods, but let me imagine it looks like that just for fun. Okay, so here's an open neighborhood containing X. Does it pick up a rational number, which is not X, if it were the case that X were rational? So again, we want to ignore X. Do we have rational numbers in here? The answer is yes by density. So let me write that. By density, the set of accumulation points is going to be all of R. Okay, this is not formal notation. I'm just using that as lecture shorthand. Let's jump right into the set of integers. With integers, we are, of course, looking at these discrete points. You know what integers look like, so there they are. And let's consider two cases. You might see the answer right away, but just in case you don't, I want to give you the full argument here because it's important that you understand this example. Let's start by considering an integer itself. So let's say that that integer is the point I would like to test to determine if it is an accumulation point for the set of integers. Can you draw an open neighborhood around X which does not pick up any other integers? And the answer is, of course. Just pick radius 1/2. And while this set contains exactly one integer, X itself, that's not eligible for like the intersection that we're trying to assess. There are no other integers in this neighborhood, so X is not an accumulation point. Okay, hope that was clear. Right, so this neighborhood does not pick up any other integers. All right, so no integers are accumulation points. What about things which are not integers? Like this point y, sitting between two. You design a radius that cuts, say, halfway to the closest integer. You could write down a prescriptive way to do that. In this case, I have to make it kind of small. But that neighborhood doesn't contain any integers at all. It has completely empty intersection with a set of integers. So in this case, there are no accumulation points. The last one is the Archimedean set. And when we met this set, I believe then I compared it to Z and said it has some things in common, but it's not really identical in nature to the set of integers. So take a moment, pause to assess this set. So look for its accumulation points. All right, what we have here is a set which consists of separated points like Z, except they cluster up around 0. And that behavior makes this set topologically different from Z. Okay, so this set, it has 1, a half, a third, a fourth, a fifth, sixth, da, 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 da. Right? It gets forever closer and closer to 0, but doesn't actually contain 0. All right. I'm not going to run through every single case, but you can imagine, if you're out here, cut halfway to 1. If you're at one of these Archimedean points, you're kind of like being at an integer in this previous example. So, you can cut kind of halfway to the nearest point. If you're over here in negative numbers, cut halfway to 0. No point away from 0 is an accumulation point. I did that kind of quickly, but hopefully your study of the set confirms that for you. On the other hand, if I pick 0, every neighborhood I draw around 0 is going to pick up a member of the Archimedean set by the Archimedean principle. That's why I call it the Archimedean set. So there we go. All right, so any open neighborhood like this is going to pick up points from the set. It so happens that 0 doesn't belong to the set, but that doesn't matter. We don't care about whether or not 0 belongs to the set. We only care about the fact that open neighborhoods around 0 pick up other points from the set, meaning points from the set in this case. Okay, so this is kind of a neat example compared to the previous ones. I mean, they're all neat, but this one is just a single point. All right. let's take a minute and just talk through whether or not these sets are closed. I just want to state the answer to that question. We will come back to that perhaps after we connect closed sets to accumulation points, but let's start to build up some observations. This set is not closed. This set is not closed. This set is closed. This set is not closed. Now that I've done that, I'm kind of laughing because none of them is a really good example of the theorem that we will prove at the end. But we have not closed, not closed, closed, and not closed. This one is kind of a funny example of a closed set with accumulation points because it has no accumulation points. So just to give you a more classic example so that I'm not going to laugh at every single example I picked, I guess I picked interesting ones. Take a moment to verify that the set of accumulation points for the closed interval from 0 to 1, so if I replace this parentheses with a square bracket, that would be the closed interval from 0 to 1. Maybe I'll write that over here. So like APs of the closed interval from 0 to 1 is the closed interval from 0 to 1. There we go. This set is closed and there's its accumulation points. Okay. Yeah. Pattern not so clear yet, but we will have a link between whether or not a set is closed and its family of accumulation points after we do 4 more examples. These last 4 examples are going to be a subset of the xy plane, any subset of a discrete metric space, the empty set, and then the entire metric space where I'm not going to specify what the metric space is. Okay, so let's start with this subset. It's really the set of points, which is the graph of the function y equals sine of 1 over x, where the domain in question is positive x. If you haven't graphed this function, you might want to pause and just see if you can create a picture of what this looks like in the xy plane. I'm going to go ahead and do it though. That's just a quick illustration. This is composition of sine and 1 over x. So let me first just imagine 1 over x for positive x values. That's this hyperbola piece. Okay, what happens if I take these values and plug them into the sine function? Well, as x goes to infinity, 1 over x goes to 0 through positive numbers. So that means we're going to be approaching, let me just draw another picture. We're going to be approaching, if I look at the circle, we're going to be approaching 0 like this. Okay, so that's kind of like decaying to 0 from above. Okay. On the other hand, as x approaches 0 from the right, 1 over x is going to go through the values pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. What I'm going to say is we're going to revolve around and around the circle forever. So this is going to take us through every revolution going that way. Okay, so that means that what we're essentially going to do is like take all of the oscillations of the sine wave and flip them so that they cluster up around 0. So that's going to look like gets increasingly frequent and then kind of clusters up around the y-axis. Not the best picture, but hopefully that makes sense. Okay. So decaying function, and then it's going to oscillate infinitely many times as we approach x equals 0 from the right, and then it's just going to oscillate faster and faster. Okay, and that's because 1 over x is going to go through like multiple revolutions of angles that we plug into the sine function. Okay, so what's the set of limit points here? What I mainly want to do with this example is just remind you to change the shape of your open neighborhoods depending on the metric space. So before our open neighborhoods looked like little intervals, so it might be tempting to be like, okay, well, let's draw a little interval like that. I just say that because I've seen students do this in the past. You have to remember, we're working in R2, so my neighborhood looks like this. Okay, so imagine I take any point that's on the graph of this function. Is it an accumulation point for this set of points? So for all of the points that live on this graph? The answer is yes, because, let me draw it here where it's flat. Any neighborhood I pick is going to pick up other points from the neighborhood. So for example, this one. It doesn't matter where we are. If I'm down here at some minimum, my neighborhood is going to have to go up. And so if I'm at the minimum, I go up and I pick up points above. So all points belonging to the set, let's call this set A, all points of A are accumulation points of A. What about if you are not a point of A? Here, we might want to think of a few different scenarios. If I'm out here, not an accumulation point, right? Because I can design a neighborhood around this point that does not intersect our graph. Same thing if I'm over here, any kind of point which has a negative x value. Around that point, you can draw a neighborhood so that you only go, say, halfway back to the y-axis. That's not what I've drawn here, but I drew one with a smaller radius. This neighborhood is not going to pick up any points from the sine function that we graphed. Is there anything, though, that I haven't considered? And the answer is yes. Okay. Let me first start, maybe if I'm here, kind of closer, anywhere close to the sine curve, you can always draw a radius that doesn't quite overlap. What I am missing is what we are approaching with this oscillation on the y-axis. So if I look here and here, from, say, y equals -1 up through y equals 1, no point on the y-axis belongs to the set A. But if you trust this picture I've drawn, or if you have a better one handy, any neighborhood I draw around such a point, so like here, I draw a neighborhood around it, I'm going to go to the right. You can see that. I go to the right, and as soon as I go to the right, some of the, in fact, infinitely many of the oscillation waves are going to live in here in this neighborhood. Okay, so the set of accumulation points is going to be A itself together with 0 through 0y, where -1 is less than or equal to y is less than or equal to 1. Okay. Right, so my goal with that example was, one, to have you sketch this picture if you haven't seen what this function looks like before. It's just a nice function to work through because you have the composition of this kind of inverting hyperbola shape and the sine wave. Okay. And then two, just to remember that in different metric spaces, we need to make sure our neighborhoods respect the kind of ambient space. All right, let me pause in case you are still thinking through this example. Go ahead and reach a nice stopping point with it. And then we will look at the second example. So here, imagine that we are in any kind of discrete metric space, and you take any subset. If you like, the discrete metric space could be these markers together with the discrete metric, and consider the set, which is just the pink marker. What is the set of accumulation points for this set? The answer to the second example is the empty set. So there are no accumulation points for any subset of a discrete metric space. And this argument is going to feel kind of similar to the integers, and there's some reasons why. So you might want to tie the integers, which is a subset of R, to this kind of feeling of describing discrete items. Anyway, I'll set that aside for now. Here's a nice illustration of why there are no accumulation points in a discrete metric space. And that is, take any point in a discrete metric space and draw a neighborhood of radius 1/2 around it. No, I don't want, I was about to say for all epsilon, but no, I just said what the epsilon is. It's 1/2. For all x in the metric space, the neighborhood around x of radius 1/2, take away x, is empty, because the only point in the discrete metric space whose distance to x is less than 1/2 is x itself. In other words, I phrased it here as an epsilon neighborhood, but this is really just a way of saying the singleton element x. That's an open set in a discrete metric space. So x, take away x, is the empty set, which means if you try to intersect it with anything, you're going to get the empty set. So there are no accumulation points in a discrete metric space. Thinking a little bit more philosophically about what that's telling us, we haven't talked yet about like where you find accumulation points in topological arguments, but often we find them when we start looking at sequences, and this idea of like limiting towards something or accumulating near something or clustering up near something. There's this idea that accumulation points allow us to characterize points as being near other objects. Let me just kind of go way off on a tangent. If you think back to the picture I started with, where I was like, here's x, and I had a U around it that was sort of funny shaped. And I said, here was a point in the set A in question. Well, I have to be able to find a point from the set in any open set around X, which means if I get smaller and smaller with my open sets and I just zoom in on X, I'm always going to be finding points from A. So accumulation points are saying like, we're always going to be able to find points from the set arbitrarily close to X. There is no notion of closeness in a discrete metric space because the only element close to X is X itself. The distance from X to X is 0. The distance from X to anything else in the discrete metric space is 1. So there's no idea of points getting closer and closer and closer to X. It can't happen in a discrete metric space. Okay, just to make sure we understand this, and because I really enjoy having discrete metric space examples, go back to the very first set we assessed, which was this interval from 0 to 1. I situated this on R, right? So we're like, okay, here's R, and here's this interval. What if my metric space was all real numbers equipped with the discrete metric space? Sorry, equipped with the discrete metric. So my metric space is R, but with the discrete metric instead of the Euclidean metric. Then we don't want to imagine our neighborhoods looking like they did. This is the same idea of you have to adjust your notion of neighborhood when you change metric spaces. This is not what a neighborhood looks like in this set with the discrete metric space. So if this set is in a metric space with a discrete metric, sorry, I need a break, so I'll step aside and let you think about the fourth example. It has no accumulation points whatsoever. So that's the conclusion of this one. So when you're looking at any subset of a discrete metric space, there are no accumulation points. Okay, yeah, I'll go have a glass of water and leave you to think about the empty set and M, and then I will come back and we will discuss these two. We'll have a really nice statement for the empty set. You can probably imagine what that's going to be. And for M, I threw that on this list of examples because I included M when we talked about open and closed sets, but here our conclusion is going to be a little different. Okay, for the empty set, probably not a surprise, the answer is the empty set. And the argument is going to be for all X and M, and for all epsilon greater than 0, you don't have to say for all epsilon, you can just pick one. We just need one counterexample neighborhood, but let's just proceed with this. The epsilon neighborhood around X, take away X, intersect A, but here A is the empty set, is the empty set. Okay, so that's me formally writing out something that probably seemed immediately true. So there are no accumulation points for the empty set. What about M? You might have been tempted to say M or something like that just because that was the answer when I asked you about M and we were looking at the properties of being open and closed. Here, the answer is we can't say without more information. If M is Rn, then the answer is M, right? So the set of accumulation points for the Euclidean real line is the Euclidean real line. If M is a discrete metric space, the answer is the empty set. If M is, let's say, the Archimedean set and only the Archimedean set, the answer would be the empty set again. But if it was the Archimedean set together with 0, it would be 0, which is just a proper subset of M. So basically the point is that I have no conclusive statement to make here about the entire metric space without more information. Okay, let's move away from examples now and link the notion of collecting accumulation points to that of finding closed sets. We will wrap up with this useful theorem. I've put up here the traditional language as well as my preferred characterization of this theorem. This is an if and only if statement, and what it tells us is that a set A is closed if and only if all of the accumulation points of A belong to A. So A contains its accumulation points. I don't love that phrasing. This is the traditional language for this statement, but I don't like it because sometimes there are no accumulation points. So I like this alternative characterization instead, which is a set A is closed if and only if there are no accumulation points of A in the complement. So if you found that X is an accumulation point of A, X must belong to A. It cannot be an A complement. Okay, let's prove this. And I will wrap up at the end by revisiting the sets that we analyzed, and we will see why this theorem agrees with our examples. Okay, this is an if and only if proof, and we will be able to prove both directions simultaneously. So I'm not going to break this into two directions. Notice, okay, so I'm just going to do like a chain of implications here, which are forwards and backwards at the same time. We want to say that A is closed and then move from that to another characterization. So A is closed if and only if. Now you might have some intuition about closed sets, but at the moment, there's really only one thing that we can definitively say about closed sets, and that is the definition. So that's really all we've covered at this point. A is closed if and only if A complement is open. We have to go there. Okay. Let's work with this notion now. What does it mean to say that A complement is open? I'm going to go straight to the definition of open. If A complement is open, then every point in A complement lives inside of an open neighborhood U, which stays inside of A complement. So this is equivalent to the definition of being open. So if and only if, for all X in A complement, there exists an open set U such that X is in U, which is a subset of A complement. In other words, X is an interior point of A complement. We are almost done. I just want to translate this into the actual language of accumulation point. So while this communicates the idea that X isn't going to be an accumulation point of A, I really want to get all the way there. Don't make the reader finish the argument. So what I'm going to do is basically restate this, but instead of saying, hey, look, X is a subset of A complement, I'm going to say it has empty intersection with A. Okay, so let's see. It's going to be if and only if because I'm just restating this and changing how we characterize this last bit. So if and only if for all X in A complement. I don't like writing there exists open, but since I wrote it out here, this is fine. So there exists open U such that X is in U and U intersect A is empty. And that is because it lives inside of A complement. I think I just want to write one more thing, but if you're kind of working through this, let me pause here, get to this point, make sure you definitively agree with it, see if you can finish the proof, and then I will come back and write the last line. All right, if you were working through this argument, you might realize now that we have it. I'll talk through both directions in a second, but let me go ahead and write it. For all X in the complement, X is not an accumulation point of A. All right, let's just make sure this if and only if works because this was just definition, this was restatement. Here, from here to here, so forwards direction, if there's a neighborhood of X which has empty intersection with A, X cannot be an accumulation point. So forwards direction is true. Going backwards from this statement to this one, if X is not an accumulation point of A, then there exists a neighborhood of X so that when I pop X out of it and look at the intersection of that punctured set and A, that's empty. But actually, since X is not even in the original set, I don't have to puncture it. So if X is not an accumulation point of A, that means that there's a neighborhood of X which has no intersection with A. So that's going backwards. Okay, that might have been a little bit of overkill, but basically we are done. I might throw one more line on here to try to go back to the original language of this theorem. So let me add, this means if Y is an accumulation point of A, then Y is in A. AP of A. Okay. If Y is an accumulation point of A, then Y is in A. If that's true, Then if X is in a complement, it can't be an accumulation point, and then vice versa. This is really a restatement as well. Okay, that wraps up this proof. Going back to our examples, let's think through them. Maybe I can resketch some of them over here. We had this example is a subset of R. This is not closed, right? If I drew in the 1 here, it would be closed, but without 1, it's not closed. And indeed, 1 is an accumulation point of this set, which does not belong to the set. It belongs to the complement. So this set was not closed. What was the next example? It was rationals, I think. When we look at the set of rationals, we said that every point on R was an accumulation point of rationals, including irrationals. So they are accumulation points of rationals which do not belong to the set of rationals. We know the rationals are not closed. The set of rationals is not a closed set. Integers is kind of a neat example. So let's see, Q. Integers are closed, but we said the set of accumulation points was empty. That's the sort of like the version of this first statement makes me unhappy because of that. So I like the second one better. There are no accumulation points for integers in the complement. So if you found an accumulation point for the set of integers, it can't be in the complement. Okay, so integers closed. We had the Archimedean set. This is not a closed set. And indeed, we found that it does have an accumulation point, the point 0, which belongs to the complement. Then we had that graph of that sine of 1 over x. That's not a closed set. That one might not be obvious, but here we can apply this theorem now to say, hey, that's not closed because its set of accumulation points included points on the y-axis, which didn't belong to that set. Discrete metric space, let me just write D and S. Actually, like integers, there are no accumulation points whatsoever. So if you have a set in a discrete metric space, you cannot find an accumulation point for it in the complement. And then I'll leave empty set is closed, kind of same thing here. And then M is not an interesting thing to study without more information about M. All right, on the other hand, if I look at, let's just squeeze it in here, 0, 1, and for a different set, how about 0, 1, union 2? Here, the set of accumulation points is a subset of R, is the set itself. Here, what's the set of accumulation points for this set? Okay, it's just the closed interval from 0 to 1. So this isolated point out here, 2, is not an accumulation point. This is closed, this is closed. For both of them, you cannot find an accumulation point in the complement, right? So here, the set of accumulation points is the set itself. Here, it's a subset. But no point, which is an accumulation point for either set, lives in the complement of that set. Okay, I will just mention as a last remark that I use the word isolated point. A point in a set is isolated if it is not an accumulation point of that set. So I'll just throw that definition into the end of this lecture and then we will stop. So this point 2 out here, it belongs to the set, but it's not an accumulation point of the set. So this is an isolated point. It's the only one from this family of examples. Coming over here, there's no isolated point. There's no isolated point. Every point is isolated. Every point in the set is isolated. None of them are accumulation points. And in a discrete metric space, every point is isolated. Okay, let's wrap this up here. We have more notions to look at, including the closure of a set, the boundary of a set. So we will continue on with this material in the next video.